Hi, I'm Nina Dang Niem. I'm a postdoc in the group of Michal Osmaniak at Warsaw. Today, I'll tell you about robust quantum advantage using fermionic linear optics and magic input states. This is a joint work with Michal Zoltan Zimbaras in Budapest and Mauro Morales in Sydney. I first motivate the notion of quantum computational advantage or quantum supremacy by sampling problem and introduce our Fermion sampling scheme, and then present our main results and how they support the supremacy conjecture. And I will summarize everything again at the end. So introduction and motivations. Quantum supremacy is the ability of a quantum system to perform a task that is infeasible for classical computers, regardless of whether the task is useful or not. Sampling problems can be used to demonstrate quantum supremacy with as few assumptions as possible. The canonical example is boson sampling, where you put indistinguishable bosons, usually photons, through a linear optical network, and look where the photons land at the end. However, the leading candidate of the quantum supremacy proposal is the random circuit sampling due to its rigorous hardness guarantees. As the name implies, you pick a random quantum circuit by, say, choosing 1 or 2 qubit gates randomly, prepare input states in the computational basis, and then measure in the computational basis also. And this has been demonstrated experimentally on Google's 53 qubit Sycamore processor last year. In this work, instead, we proposed a quantum advantage scheme using fermion sampling with magic input states. This is an analog of boson sampling, but more suitable to circuits. The two main differences between this and the random circuit samplings are that, one, the quantum circuits are restricted to the so-called Fermionic Linear Optical gates, from now on abbreviated FLO gates. It is well known that FLO, when restricted to computational basis input state and output computational basis measurement, are efficiently simulable classically. Thus, the second difference is that instead of fermion number states, we input entangled so-called magic states in each block of 4 modes or 4 qubits. The number of blocks is denoted by capital N, and this will be the main parameter that we associate with the system size. So for each block, the state can be prepared by a few entangled gates. Before our work, the schemes can be seen to be a candidate for a quantum advantage scheme because of the following reasons. For full active FLO, the addition of magic state promotes it to universal quantum computation. And even when restricted to the number preserving or passive FLO, this also, the magic state also leads to probabilities that are hard to compute in the worst case, which is necessary but not sufficient for quantum advantage scheme. A practical advantage of our scheme is that these passive or active FLO circuits are already natural restricted set of gates in the existing superconducting qubit architecture. For example, the 2-qubit fermionic swap gates can be realized with high fidelity, say compared to CNOT, in the demonstration of random circuit sampling on the Sycamore processor. Also, the same processor can be used to do useful tasks, such as a proof of principle quantum chemistry calculation and some algorithm for optimization problems. Now I'll show you our technical results that justify fermion sampling as a quantum advantage scheme. First of all, I have to introduce you to the group structure of FLO that are crucial to arriving at our results. We will always use D for the number of fermionic modes. D fermionic modes are described by D pairs of creation and annihilation operators, which respect these canonical anti-commutation relations. or equivalently to the Majorana operators, which are Hermitian linear combinations, which are analog of, say, X and P for bosons. If you stack these 2D discretion and annihilation operators into a 2D long vector, then the group of passive FLO acts exactly as a unitary matrix on this vector that do not mix creation and annihilation operators. So they're from the unitary group UD. Whereas active FLO are circuits generated by Hamiltonians that are quadratic in the Majorana operators with the bilinear forms skew symmetric matrices that generate rotations in 2D dimension. So they form this spatial orthogonal group, SO2D. Crucially, even though the dimension of the Hilbert space that this group represented as unitary circuit is exponential in the number of modes, but this group can be described only by poly-D parameters, and this will be crucial to, for example, our results on robust worst to average case reduction, hardness reduction. Now, let us talk about what we have to show to support the quantum supremacy conjecture. Suppose that we have a classical machine that samples from the output distribution of our circuits. If we have something called the anticoncentration property, which I will explain in the next slide, then the classical sampler can be leveraged in a certain low level of the so-called polynomial hierarchy complexity class to produce a good approximation to the output probabilities on average, meaning average over all FLO circuits. Therefore, if these probabilities are sharply hard to approximate up to these errors we have, then the polynomial hierarchy collapses to a low level, which is widely believed by computer scientists to be false. And therefore, by following this change of logic backward, then this classical sampler cannot exist. What we actually prove, and this is similar in previous works up to today, is the average case hardness up to some error which does not yet imply the supremacy conjecture, but support the conjecture. Our first result is the anticoncentration property, which roughly means that each output probability is not too small for a large enough fraction of FLO circuit. And here is the formal statement. To arrive at this result, we use the Pauli-Sigmund inequality, which requires to calculate the second moments, and that can be calculated using group theoretic properties. We do not use the 2D psi property, and in fact, it can be shown that the Haar measure on this group of FLO do not form a 2D psi. Also, numerics suggest that these output probabilities do not anticoncentrate if the input state is Gaussian. Our second result is the average case hardness of approximating the output probabilities of our scheme. So the goal here is to construct a low degree rational interpolation between a circuit that expresses the worst case sharply hard probabilities and generic circuits. Why? Because then we can use existing polynomial interpolation technique to recover the value of the worst case probabilities from those of generic circuits. And therefore, if the worst case property is hard to approximate, then those of generic circuits are also hard on average. To achieve this goal, we use the state-of-the-art approach of Cayley path deformation by Movassagh, which interpolate between two group elements using these rational functions shown here below, where theta is the interpolation parameter. When theta equals 0, we get a group element that is represented as a worst case circuit on the Hilbert space. And when theta equals 1, we get a circuit that is uniform or Haar distributed. And for our value of theta between 0 and 1, this path always lies in the group, meaning that the circuits are always unitary. The main difference to previous work is that instead of deforming 1 and 2 qubit gates at the level of physical circuits, we deform at the level of the group element, which is then represented as a global circuit while maintaining the low degree structure. Here, the degree are quadratic in the number of magic states. To emphasize, if we apply this technique to random circuit sampling, which happens in the exponentially large hyperspace, the degree of the rational function will be exponential. The polynomial degree in our case is precisely because the group of FLO circuits are polynomial size in nature. And so we have the result that it is sharp p-hard to compute the value of output probabilities with for an appreciable fraction of all FLO circuits. Also similar to previous work, this hardness results can also be improved to the average case hardness of approximating these output probabilities up to some additive errors. To compare with previous result by Movassagh, our degree of approximation is slightly worse. And here's the degree that's, and here's the error that's required for the supremacy conjecture to hold, which all of the work up to date have not yet achieved. Our final result is the certification of the FLO circuit. Assuming that the circuit is FLO, then we show that the circuit can be efficiently estimated using single mode input states and computational basis measurement. And the sample complexity of this test is efficient, meaning here specifically polynomial in the number of modes and inverse polynomial with the estimation error in the diamond distance. To conclude, we propose Fermion sampling scheme with magic input states, which utilize gate sets and architecture native to superconducting devices and has the potential to be realized in near term. We provide the state-of-the-art hardness guarantees by proving anticoncentration and robust average case hardness of computing the output probabilities. The hardness guarantees are comparable to random circuit sampling and surpassing Boson sampling. Both results are derived using the group structure of FLO circuits and has the potential to be a technique to be generalized to other groups. And assuming that we have an FLO circuit, then the circuit can be efficiently certified. Thank you for listening.